Okay. With great difficulty I have been able to draw this circuit, which is complicated, and the board also is not very good, it is very deceptive. Anyway, let us start this. I first have drawn that adder. This is the adder which has a adder unit plus one pipeline latch which is shown separately, one input which is switched, another input which is switched. Then I have drawn one R1 with input switched output and R2 with input switched output, then a multiplier that has, sorry, this is a multiplier, this is not be, this is not an adder, by mistake I have drawn as adder, it is actually a multiplier. Okay. All right, this multiplier one input which is built-in constants A, B, C, D, that you can see A is for a multiplier 5, multiplier 5 schedule is 0, that schedule 0, it touches A, then takes acts as multiplier 5 and takes this input as A. Then next is 8, 8 means this fellow D, this multiplier which is built-in constant D and schedule is 1. So, next is schedule 1, that time it takes D, then schedule 2, schedule 2 is 6, multiplier 6 has constant B. So, B is at schedule 2 and lastly 7, multiplier 7 has constant C, its schedule is 3, so schedule 3 C. All right. Now, let us see how we have drawn this circuit. Let us start with N1. Okay. N1 you see, N1 is born here, okay, in cycle 4, and cycle 4 in modulo notation, we are, I mean, Parhi's book uses modulo notation. So, 4 is equivalent to 0 because 4 modulo 4 is 0. Why modulo? Because every 4 cycle constitute a block. So, if it is a 5, that means 4 cycles done and 1 more. So, it is the cycle 1 of the next block. So, it is modulo conversion, you restrict yourself in to this either cycle 0, 1, 2 or 3. It could be for the next block or next to next block, does not matter. Okay. If you, that is the notation that this book by Parhi follows, and I am just sticking to that here, but if you are not comfortable, you can write 4 as well instead of calling it 0. But I am following this book so that there is no confusion, instead of 4 I will write as 0. So, at cycle 0 which is equivalent to 4, N1 is born. This N1 as per this diagram, N1 born, it will go to R1 input. So, that is why this switch comes here, it goes to R1 input. Now, one thing you see, as N1 is born, even the cycle 4 itself, that is without being stored, it goes to 5, device 5 means multiplier 5, input of multiplier 5. That is why there is a parallel path directly going to multiplier. Okay, and this multiplier input will touch it in the same cycle 4, which is equivalent to 0. So, this will directly go here and go to the multiplier. This multiplier in the cycle 0, that is cycle 4, will work like will work for this. Okay, multiplier 5. All right, cycle 4 it is out, and 4 to 5. Okay, here. So, the same cycle it will be going there. All right. So, cycle 4 it is born, which is 0, and in the same cycle it goes to multiplier input, multiplier 5. All right. Now, after one cycle, in cycle 5, there is after being stored by register 1 R1, this is used up in 2. 2 means device 2. Device 2 is an adder. So, that is why from R1 output, this comes to here at the adder input. That time the adder is working for adder 2. And what cycle? Cycle 5. Cycle 5 is equivalently 5 modulo 4 is 1. So, that is 1. So, this is touching at 1. All right. Otherwise, you look at N7, N8. N7, N8. I will complete this journey of N1. For the timing, I have gone from cycle 4 to cycle 5. It has come here, and cycle 4 to 4 itself going to multiplier 5. Okay. So, that what I have done. Now, consider this N8. N8 is born at the output of multiplier, multiplier 8, and it goes to adder 4 after one cycle. Okay. So, N8 will be coming from multiplier output. So, from this output line, then again stored by one cycle. So, stored, so that it will touch this here at what cycle? Cycle 3. Cycle 3, N8 is born. So, if it touches this, it will take the multiplier output, which is this fellow N8, okay, cycle 3. It will be stored in R1 and then consumed. But after being consumed, where will it go to? 4. 4 is an adder. So, that is why it is going here to this input again. Okay, that time it is working the adder 4. Which schedule? Which cycle? Cycle 4, which is equivalently 0. 4 modulo 4 is 0. That is this 0 standing for. And consider again N7. Basically, I am considering storage by 1. Here storage by 1, storage by 1, storage by 1. 4 to 5, 5 to 6 and 3 to 4. Okay, this storage by 1 is done by R1. I am just considering that storage by 1 cycle. So, now again N7 born here in 5 and it goes is stored by R1 and then consumed. It goes to 3. 3 is an adder. So, again it will go to adder and is born in 5. That is why, and 5 is 5 modulo 4 equivalently 1. That is why this multiplier output is coming here, this R1 input touching there at 1, that is 5 equivalently, and the output is coming here. Okay. In the next cycle, what is the next cycle? There is 5, it is born 6. 6 modulo 4 is 2, that is this 2. Okay. So, this N7, N8 done, all right, N7, N8 done, and N1 I went from 4 to 5, all right. Now, consider 4 to 5. So, 4 to 4, that is when it goes going to multiplier 5 done, then 4 to 5 R1 output going to adder 2 done, then one more cycle 4 to 6. Now, what is happening? Look at this table. 4 it goes to the input of R1. So, it cycle 5 it comes to the output of R1 and is stored 2, then it is giving to R2. Okay, R2. So, cycle 6 it will come to the output of R2. Okay. So, if it is at 4, this fellow will touch it, okay, which is 1, 1 means 5, at cycle 5 it will touch, it will come here at R2 output. At what cycle? Cycle 6. After that, what is happening is this, cycle 6, okay, and it is fed back to the input of R2 itself. So, it is fed back, it is cycle 6. 6 is equivalently 2, 6 modulo 4 is 2. Then it is stored by R2 itself, it goes to the output of R2 at cycle 7. Cycle 7 means cycle 7 modulo 4, that is 3. So, at 3 it comes here, all right, and then again it is stored 8, all right, cycle 7. So, 7 it comes here, then 8, cycle 8 is equivalently 0, 8 modulo 4 is 0, 0 again it is stored, and finally it is coming at 9, 9 is equivalently 1, all right. And during this journey what is happening? You see, after is stored by R1, then R2, it goes to 6, 6 means multiplier. So, it goes to this multiplier at what cycle? It was cycle 5, there is 1, after here cycle 6, it goes to 6. So, 6 is equivalently 2, so it goes to multiplier input at 2, then it is stored 6, at cycle 6 it is stored, cycle 6 is 2. So, one more cycle, cycle 7. In cycle 7, it is used up by again device 7, device 7 is multiplied. So, that is why it is coming here, and 7 equivalently 3, modulo 7 modulo 4 is 3. So, it is touched here at 3. Then at 7 again it is stored, okay, 7 means 3. So, 3 it is stored, it comes out at 8. 8 I do not use it anywhere, but 8 is means 8 modulo 4 is 0. So, at 0 it comes again, then it is 9. Okay. At 9 it is used up by 8, device 8 is 8 multiplier, and 9 modulo 4 is 1, that is why it is touching here at 1. So, this is the 1, 2, 3, all right. This takes care of the journey of N1. So, journey of N1, N7, N8 done, all right. Now, consider N2 I will come later because N2 does not do anything, N2 output is taken out as the output. Start with N3, N3 born in cycle 3 and dead in cycle 3. Cycle 3, so N3 is the output of adder. So, the output of adder goes out at cycle 3 and that time where does it go to? It goes to adder 1. So, it goes to the other input of adder. So, from here it goes to the other input of adder at cycle 3 I am touching it. Okay. Then comes N4, N4 also is the adder output. Okay. N4 adder output born in cycle 1 and is consumed in cycle 1. Where does it go to? Device 2, which is an adder. So, it goes to the other input of the adder at cycle 2. Okay, sorry, cycle 1, 2 is the number, cycle 1. So, again I am touching it at 1. So, 1 corresponds to this N4 being born in cycle 1 and also consumed in cycle 1, that is N4 going to N2, sorry, adder 4 output going to adder 2 input. All right, that is. And similarly, consider consider N2. N2 is the output of adder 2. Okay, adder 2 schedule is 1 and then one internal delay to schedule 2. At schedule 2, it will take me the output. So, this adder output I am touching here at schedule 2, I am taking it to be the output. All right. So, N3, N2, N4 done, N5, N6. N5 and N6 coming out of multiplier. So, multiplier output. Where is it? Where is N5 going to? N5 going to 3. All right. Who is 3? Adder. So, N5 will be going to, and born and dead in the same cycle, no need to push it through this register chain, no need to store. But N5 will be going to adder, adder 3, so other input of the adder. Okay, at what cycle? Cycle 2. So, N5 directly going to the other input here, cycle 2. N6 again going to adder 4, device 4 is adder. So, again it will also go to the other input of adder, but at what cycle? Cycle 4, which is equivalently 0, 4 modulo 4 is 0. So, output is going here at 0. All right. So, this completes the circuit, both hardware optimized, that is multiplier and adder optimized, because I am using only one adder, one multiplier, and delay optimized, only 2 delays, R1 and R2. Earlier I had about 6-7 delays. Switches, you can say that switches are more switches are brought in here, so they may use up some hardware, but the point is switches are I mean just mux, they are not FET switches or MOSFET switches, and here N is 4, but N could have been it could be a big circuit and N could have been 100. Then also number of switches could have been same. Okay. So, switches do not add to the complexity that much. Okay. So, here we stop for the folding part. We have done the folding of hardware units, then we have done some theory, retiming for folding, cuts and retiming for folding, so that no edge turns out to be negative. Then we went for delay optimization by folding, we considered lifetime analysis, lifetime chart, then forward backward data allocation, and finally construction of the circuits. We took some examples and finally worked out the same thing for a digital filter. Okay. So, I think we have given enough coverage of folding. We now consider the next topic. Okay. I will be going going back to unfolding again. We have seen in the case of unfolding, if originally one process is given to you, some job, some computation, it was taking t amount of time because critical path was t after doing whatever possible retiming you could do. Then what do? We make it parallel, right? If you want to bring down the input and output, if you want to bring up the input output rate by a factor of j, that is reduce the period by a factor of j, then I need to, but system clock won't go up by that rate. So, I need to make j copies in parallel. So, that has one disadvantage, that whatever hardware it takes, that gets multiplied by j, whatever power it takes, that it consumes, that gets multiplied by j, right. In general that is true, but in the case of certain circuits like I mean FIR digital filters, we can show some techniques by which we will see that hardware cost will not go up by a factor of j, it will go up by some fraction of j. We can have considerable hardware saving, though speed wise there is no loss, input output speed will still go up by the factor j. Now, to do this, we need to have some idea about what is called polyphase decomposition and little bit about multi-rate signal processing, very little, which we will do here. Suppose I have got xn, one sequence. This is 0th sample, this is -1, x -1, all right. Xn has a Z transform with some appropriate ROC xz. This is fine. What I do is this, now I bring in additional points here. M minus 1 points. So, what I do, I have the same sequence, same values, but it is 0, then I have got new points 0, 1, 2, dot 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 up to some m minus 1, m is some chosen integer, minimum value 1, minimum value 2. So, and at all these points I introduce 0 values. So, this will be m. At mth point, what I have, the x1 sample, earlier it was standing at point number 1, now it is standing at point number m, sampling point m. Then again I introduce zeros, m minus 1 zeros. So, mth point, then m minus 1, so there will be 2 mth point. Who is standing? Same x2. Then again 0, 0, 0, 0, 0, m minus 1 zeros. M is an integer of your choice greater than or equal to 2. So, that 2 minus 1 is 1, that is at least 1 0 is there, otherwise this exercise has no meaning. So, between every pair of samples, I introduce zeros, dot 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 dot. This sequence I call x e subscript e n. E stands for expanded, x e n expanded version. So, E stands for expanded. We denote like this, x n, let me draw it again. Still it is not coming. This is a problem with this board, very solid alignment problem on this board. This is the notation. It is called expansion. Actually, if you want to do it in real time, that means earlier maybe you had an analog waveform which was sampled, maybe an analog waveform like this. You sampled here, so these are the sampling points 0, maybe capital T, okay, in terms of time t, 2t, 3t, minus t, and like that. Now you are creating intermediate sampling points. So sampling period now is only this much, t by m, but you do not have the samples, you do not have this value, you do not know, because it came and you took samples and signal has gone. So I am just putting 0 values. I am not approximating this waveform, I am just putting 0 values. But from this analogy you can see that XEN in terms of real time operation can be viewed as a faster sequence, faster by a factor capital M. The period has gone down from capital T to T by M, okay, T by M. So it is a faster sequence and faster by a factor capital M, all right. Then what is the Z transform of XE? This is nothing but Z transform of this, okay. Now this fellow is X0. If you take Z transform, write the Z transform expression X0 Z to the power minus 0, because 0 is the index, then these zeros do not mean anything. The next sample is x1, but it is z to the power minus m, because sampling point has changed now, index has changed. Then again, or zeros do not mean anything, then 2mth point you have got x2. Again zeros do not mean anything, next will be 3m. So, then x3 z to the power minus 3m plus dot 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 dot, and this side x minus 1 z to the power, this is minus m down. So, minus and minus plus, so z to the power m and dot 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 dot. Suppose z to the power m I write as z1. So, this is nothing but x minus 1 z1 plus x0 z to the power minus 0 or z1 to the power minus 0, they are same. z1 to the power minus 1, x2 z1 to the power minus 2, x3 z1 to the power minus 3 and dot 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 dot, all right, which is nothing but original Z transform, but evaluated at Z1. Thus, you see this is nothing but original Z transform evaluated at Z1. Now, what is Z1? Z to the power m. So, I write this result here x e z ROC here will be a part of the original ROC. This you can find out. I will not get into that because this is not a class on DSP. This is the expression. Equivalently, if I give you, if somebody has given me xz, I replace xz, in xz, z I replace by z to the power m, that is x z to the power m. This will be nothing but x0 z to the power minus 0, which is z to the power m minus 0, which is same as z to the power minus 0. So, this I do not change. Then x1 is z to the power m. So, x1 instead of z it is z to the power m. So, this. Then again x2 z to the power minus 2m dot dot dot. So, that means I can write it as though there are terms here with 0 values, 0 into z to the power minus 1, 0 into z to the power minus 2 and dot 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 dot. So, between x 0, z to the power minus 0 and x 1 z to the power minus m, I can assume m minus 1 terms with value 0 and z to the power minus 1, z to the power minus 2 and all that. Similarly, between x 1 z to the power minus m and x 2 z to the power minus 2 m, here again I can assume 0 value into z to the power something whatever, what is that, minus m plus 1 plus so, okay, all 0 values. So, it is nothing but Z transform sequence of this kind, that is given x n, if I plug in zeros like this m minus 1 zeros between every pair of sample, then take the Z transform, that becomes same as capital X instead of Z, Z to the power m. The moment you replace Z by Z to the power m, that means in time domain between every pair of samples you have a band of zeros coming, how many, m minus 1. This is about expansion, all right. Using this, we will develop the idea of polyphase decomposition, but I think that will take some more time. I have just got 5 minutes left. I would rather not do that here, but what I am going to say is this, that the sample, this waveform, any analog waveform, when you take samples, or maybe we do not use analog waveform at all. What I will do, I am just giving you the philosophy, because in such a short time I cannot cover it today. Suppose you are given a signal, a sequence, I will select certain samples at 0th point, mth point, 2mth point, 3mth, minus mth and all that, just pick up them. That will be called polyphase factor 0. Then I will pick up sample at 1, sample at m plus 1, sample at 2m plus 1 and like that, okay, and form a sequence that will be called polyphase factor 1. Similarly, polyphase factor 2. So, you can see that maximally I will have polyphase factor m minus 1. Using them, I would be able to get back my sequence, that is what I will show, and that is called polyphase decomposition of a sequence. Each of these polyphase components will be very handy for me in the hardware, in the unfolded version of unfolded realization of a FIR filter. FIR filter have a finite length impulse response. Okay. When I try to implement it in hardware, if I do ordinary unfolding, I mean hardware cost will go up j times, but if I follow certain tricks which use this polyphase decomposition, it will not go up by a factor of j times, but by certain fraction, maybe j by 2, j by 3 or like that. Okay, this is a very interesting thing, you should, it is a very involved thing, so I will not get fully into it, but at least j equal to 2 case and j equal to 3 case we will consider. Okay. So, that is all about next day's class. Thank you very much.